Hi, this is Jeff Spence, Math 135 instructor for the Community College of Denver. We're on to 5.3 titled Conditional Probability. A lot of the theme of this lecture is going to be more on just trying to work the problems without using the formulas. I find that when we try to plug numbers into the formulas too much, it becomes harder and more confusing than it would be if we just try to work the problems using a couple key ideas. We're going to start with the key idea of independent events. So, two events, the definition of independent events here is in orange. The two events are independent. Two or more events are independent, but at this place we'll talk about two events are independent if the occurrence of the first event does not change the probability of the second event. So we're assuming that one event happens first and then it does not change the probability of the second event. So for instance, if you flip a coin, you get a head or a tail, the next flip, the probability of getting a head of a tail is still 1/2 and 1/2. If you roll a die, rolling a 6 on the first roll does not change the probability that you will get a 6 on the second roll. Those events are clearly independent. The other main thing I want you to keep in mind is when we talk about independence, in general we're talking about having multiple trials of an experiment, or even having multiple experiments where we're talking about the outcome from one experiment and the outcome from another experiment happening consecutively. But the key thing is multiple trials. And whenever we have multiple trials, we will want to multiply probabilities. Multiple trials multiply probabilities. So what we're going to do, this is a key idea. We're just going to take each individual event's probability and multiply them. So let's move on to the next page. Here are some examples of a bunch of independent events. So the first one says the probability that if you flip a coin you get a head, and the probability that you get a 6 right after that if you roll a die. So the chance of flipping a head is 1 out of 2. Next, we assume that we want to get a 6, so the probability of that when you roll a die is 1 out of 6. Multiply those two numbers. When we multiply fractions, we multiply across, and we get 1 over 12. That's the probability of getting a head and then rolling a 6 right after. Okay, next. How about if we ask what's the probability of getting a head and then a head again? Well, we know the probability of getting a head alone, and we know the probability of getting a head alone again is 1/2 and 1/2. Since it's multiple events and multiple trials, we multiply the probabilities and we get 1/4. What if we wanted to roll a 1 and then another 1? This is called snake eyes in some games, and so if the one die rolls as a 1 and then the second die rolls as a 1, well, this is pretty simple. What's the probability that the first die rolls a 1? 1/6. What's the probability that the second die rolls a 1? 1/6. Since we have multiple events, the multiplication principle tells us to multiply these two based on how many different ways, how many outcomes we can have, and this is 1 out of 36. Next, how about getting 5 heads in a row when you flip a coin? Well, the probability that you get a head the first time is 1/2. The probability that you get a head the second time is 1/2 because these events are independent. Probability you get a head the third time is 1/2. The probability that you get a head the fourth time is 1/2. And the probability that you get a head the fifth time is 1/2. It's all 1/2. So one way of kind of shortening this up is saying this is 1/2 to the 5th power. And that's 1 over 32. What about 10 heads in a row? Well, same as above, but now we're doing 10. So what's the probability that you get a head one time? 1/2. How about 10 in a row? Raise it to the 10th power. And we had this problem on our last classwork. I believe the answer is 1 out of, let me double check. I think it's 1,072. 2 to the 10th. Oh, 1,024, so I'm glad I checked. 1 out of 1,024. Okay? So these are independent events. Multiple events, multiply. Take their individual probabilities, multiply them together. Let's look at some other examples where we need to examine independence versus dependence. So, let's say we have a bag of 20 marbles, and 5 of them are red, 6 of them are blue, and 9 of them are green. So, there's 2 different ways we can select marbles from this bag. We can select them with replacement. What that means is if I select them with replacement, each time I select, I put them back. Okay, so I select, put it back, select, put it back, select, put it back. Sampling without replacement we'll do below. So let's look at the probability that I get a red, and then a red from 3 successive draws. Well, the probability that I get a red the first time is 5 out of 20 because there's 5 reds. But I put it back. So my second selection, what's the probability that I get a red the second time? Same thing. 5 out of 20. What's the probability I get a red the third time? Well, since I put that red one back, it's still 5 out of 20. And since I made multiple selections, I need to multiply probabilities. And I get 5 times 5, 125 over 8,000. Okay, and we can reduce that later. I'm just showing you how the answer would come out. Next, what if we want to select 3 marbles and we select with replacement? We get a red, a blue, and then a green. Well, the probability of getting a red, once again, is 5 out of 20. What's the probability that we get a blue? 6 out of 20. And then what's the probability that we get a green? 9 out of 20. Multiply those 3 numbers to get our answer. So we have 9 on the top, 270 on the top, over 8,000. And then we can reduce that later. All right, then the last question, what's the probability that all 3 markers that I select are not green? So three in a row that are not green. Well, there are 9 green markers. So that means that there are 11 out of 20 that are not green. But I'm talking about getting 3 in a row. So I put it back, and it's still 11 out of 20, and still 11 out of 20 for all 3 selections. So if I multiply those together, I should have 1331 over, sorry about that, 3 over 8,000. However, more often than not, in the real world, we select without replacement. We might want to use these marbles and do something with them. So let's look at this probability. This is where we really get into what's called conditional probability. So if I select a marker and put it in my, or sorry, not a marker, but a marble and put it in my pocket, that means that there is 1 less marble in the bag, which affects the probability of the next selection. This would be called dependent events. Okay, so let's take a look at this. Let's just look at the first example. So I want to get 3 reds in a row, but I keep each marble. Well, the chance that I get a red the first time is still 5 out of 20. But now I'm asking for 3 reds in a row, but I kept the first one. So if I kept that first one, how many red marbles do I have left? I have 4. And how many marbles are left total? 19. Let's say I kept that second red marble. How many red marbles are left? 3. How many marbles left total? 18. So if you multiply these together, we get 60 over 20 times 19 times 18, 6,840. The probability is very different from above. Notice when we had sampling with replacement, it was independent, 125 over 8,000. Now it's 60 over 6,840. So sampling without replacement is when events are dependent as you go down the line. This is a classic example of doing a problem without actually worrying about the formula, the conditional probability formula, and just thinking our way through it. How many do we have? How many do we have left? Let's go through the next two examples. So once again, we're sampling without replacement. We want to know the probability of getting a red, a blue, and then a green. So the probability of getting a red, 5 out of 20. Probability of getting a blue after we selected that red, well, there's 6 blue, but now there's 19 total marbles. And then the probability of getting a green, well, there's still there's still 9 green markers. 9, but there is only 18 to choose from. So notice how the denominator goes down 1 because we're sampling without replacement. Numerator is 270 over 6,840. Okay, last one. What's the probability that all 3 are not green? So notice I'm doing the same 3, but one is with replacement, one's without replacement. What's the probability all 3 are not green? Well, to start off, there's 11 that are not green, but then I'm going to keep 1, so now I only have 10 that are not green out of 19. And then lastly, I only have 9 out of 18 that are not green because the denominator goes down when I keep keeping the marbles. And let's see here, 90 times 11. 990 over 6,840. So there's a big difference between sampling with replacement, which is independent, and sampling without replacement, which is dependent, and we use the conditional probability idea that the probabilities change as we go down the line, as we go down each selection. But in all these cases we have multiple selections, which means that we're multiplying the probabilities after we write them down. Okay, now we're going to do a couple conditional probabilities from this table. This is the same table I used in 5.2. It's, say we had 50 total students and we just clocked whether they're male or female and what color hair they had. Okay, so in green, suppose the greens are the instructions. Suppose we randomly select one person from this table above, one out of these 50 people above. Now, conditional probability, it's given a condition. All right, so conditional probability kind of creates a smaller subgroup of the population that you do the probability out of. So in this example, if we randomly select one person above, but we know, given they are a female, okay, so we know they're a female, that means there are 30 females, okay? So our denominator is out of 30. We're not selecting out of these 50 people anymore because we know that this person is a female. So the total number of people is out of 30. We want to know what is the probability that they have brown hair. Well, once again, we're only in the female row, and the number of females that have brown hair is 6. So it's 6 out of 30, which you could reduce later to be 1 out of 5. Okay. Next, let's flip the condition around. So let's assume that they are given that they have brown hair. Given that they have brown hair. Now, the number of people that have brown hair is 14. Okay, so we're assuming we're only selecting from the people that have brown hair. What is the probability that they're female? Well, there's still 6 females. Sorry, let me do the denominator. It's out of 14 people. But there's still 6 females with brown hair. So our numerator is 6. Okay, and conditional probability, the book stated, is like kind of selecting from a subset of the population. We're not selecting out of 50. We're selecting out of the given condition, whether it's female, brown hair, male, blonde hair. We can change the given condition for any question. Okay, to summarize this section, I'm going to do the table, do a few more problems from the table, and I'm going to actually ask questions that I could ask really from this whole chapter. Okay, so we have the table again. Suppose we randomly select one person. That's the instructions in green. First example is, what's the probability that they are blonde and female? Well, I want to know the probability that they're blonde and female, so they have to be both blonde and female at the same time. How many blondes are females? Well, that is this number 11, sorry. And the 11 is out of the 50, the total, because there's no given condition. So that's 11 out of 50. because we're randomly selecting somebody from the table. There's 50 people. There's 11 that are blonde and female. Okay, now the next question, this is actually from 5.2. What's the probability that they're blonde or female? So that's very different from blonde and female. We're asking for blonde or female. So we have to take the total number of blondes, which is 16 out of 50, add it to the total number of females, which is 30 out of 50. But what happened? We counted this 11 that I have circled twice when we counted the blondes, and then we counted the females. We counted it twice. So we have to subtract that off, minus 11 out of 50, and we'll get our answer. 16 plus 30 is 46, minus 11, 35 out of 50. That is the addition rule from 5.2. Okay, let's go back, or let's do some conditional probability now. I don't know if I said that last one. That was the addition rule, sorry. So the next example, given that they are, so remember, suppose we randomly select one person, that's in green. Third example, given that they are female, so now we are only out of these 30 females, only out of those 30, because that's the given condition. Given that they're female, so we're out of 30, what's the probability that they're blonde? Well, there's 11 blondes that are female, so 11 out of 30. Lastly, suppose we randomly select one person, but now we know that they are blonde. The total number of blondes is 16. We know that they're blonde. What's the probability that they're female? Well, there's 11 females that are blonde, 11 out of 16. So, to summarize, the main point about this presentation, especially this last table, is to show you that there's really only one formula that you really need to remember, and it's the addition formula right here when we have the word or. You do the probability of each one, and then you subtract the probability of both of them happening, because we actually count it twice. But we're also going to do problems that are conditional when we give a condition, and that's like creating a subset. That's why both of these were out of a smaller number than 50, out of 30 and out of 16, because that's what the given condition was. If we go back to some further examples where we select with replacement or select without replacement, you have to remember that when you select with replacement, the denominator is the same each time because you keep putting back the marble. So that those problems are much easier. Since we make multiple selections, we take each probability and multiply them. Selecting without replacement is where the denominator goes down one because we keep losing, or we keep holding on to a marble, but we still multiply the probabilities as we go down because it's multiple events. Just the probabilities change as we move down the line. Still pretty basic, as long as you don't try to fit all these numbers into a formula. Back here are a bunch of independent events, meaning that the probabilities don't change as you go, or as one event occurs, the probability of the next event doesn't occur, and we still multiplying probabilities. So that's the summary. Good luck. We'll see you in class.